Okay, well, what do you say we get a little practice in here on solving an and compound inequality? Now, a compound inequality consists of two inequalities joined together by and or the word or. And if we're going to solve a compound inequality, we've got to solve each part of the inequality. Now, the difference between an and an or is the and is the intersection, the common ground, if you will, that we find within the inequality. And or, which we'll look at a little bit later, is the union, the joining together of the two inequalities. So let's see. Let's start here on the first one. Now, your book gives you a couple of methods to do it, where you solve each of them separately, and then it also talks about solving them together. I don't really like the solving together. You have an example of it there in the book. If it fits you better, go for it. But I prefer to actually separate them. So let's see. We got this. We got negative 12 is less than or equal to 4x plus 8 and 4x plus 8 is less than or equal to 32. Now, one of the ways that I can recognize that this is an and inequality is that this expression right here is sandwiched in between these two inequality symbols. If it was an or statement, it would actually just say or. Now, you can sometimes come across some compound inequalities that actually use the word and, but most often than not, you see it sandwiched in like this. So if I'm going to solve these things separately, I'm going to set it up like this. I'm going to set up negative 12 is less than or equal to 4x plus 8. And I'm then going to turn around and set up a second scenario where I've got 4x plus 8 is less than or equal to 32. All right, so let's look at these one at a time. Well, I got negative 12 is less than or equal to 4x plus 8. I want to get my constants all on one side, so I'm going to subtract 8 from both sides. And when I do, I'm going to have negative 20 is less than or equal to 4x. I want to isolate the x. I'm going to do the inverse of this multiplication. 4 times x. I'm going to divide both sides of the equation by 4. And when I do, I'm going to have negative 5 is less than or equal to x. All right, now let's work on solving this second portion over here. So here we got 4x plus 8 is less than or equal to 32. Well, I'm going to subtract 8 from both sides. So I get my constants all on one side. And then when I do, I'm going to have 4x is less than or equal to 32 minus 8 is 24. And we're going to divide both sides of the equation by 4. And x is less than or equal to 6. Okay, so now comes the part I got to sit here and think about. And that is, so I got x is, and I'm going to rewrite this to be x is greater than or equal to negative 5. So I've got a scenario here. I got a compound inequality where x is going to be greater than or equal to negative 5, but it's also going to be less than or equal to 6. Let's see how I want to show this. And since it's an and inequality, I'm just looking at what these two have in common. What is the intersection? But if I were just to simply graph this first part right here, where x is greater than or equal to negative 5, and let's say that's negative 5, well, my graph would be going this way. Okay, at a negative 5 mark. And if I were to graph this second portion right here, where x is less than or equal to 6, let's say this is 6, my graph would be going this way. But in order to accurately represent this entire expression here, or this compound inequality, I'm going to have a number line. It's going to look like this. Let's say that I've got 6 right here, and I got -5 right here. Now let's see, I didn't do much. I didn't do any thinking about open dots and closed dots on those first two. Well, they're both going to be closed dots. So here I've got x is greater than or equal to -5, but at the same time, x has got to be less than or equal to 6. So we're going to put closed dots on both ends of these. And simply, this is my correct representation for an and compound inequality. We'll look at one more. All right, let's look at a second example solving an and compound inequality. And let's go right here. So let's say we got -5 is greater than or equal to, and your book shows a 3z, but I don't like the z. I'm going to stick with an x. 3x minus 2. And that 3x minus 2 then is also greater than -14. All right, so I know it's an and compound inequality because I see this expression right here sandwiched in between those two inequalities. That's giving me a major signal that this is an and compound inequality. And so I'm going to break these down into two parts. So I'm going to go over here. I'm going to have -5 is greater than or equal to 3x minus 2. And then over here I'm going to go with 3x minus 2 is greater than -14. And then I'm going to solve both sides of this. So let's see, I'm going to go to the one on the left here. -5 is greater than or equal to 3x minus 2. I'm going to add 2 to both sides. That's going to end up with -3 is greater than or equal to 3x. And I'm going to divide both sides of the equation by +3. And when I do, I'm going to end up with -1 is greater than or equal to x. And I'm going to go ahead and just rewrite this where the x is less than or equal to -1. Now let's work on the second half. So here I got 3x minus 2 is greater than -14. I'm going to add 2 to both sides. So then I'm going to have 3x is greater than -12. I'm going to divide both sides by 3. And x is greater than -4. All right, so this is an and compound inequality. I'm looking at the intersection. Where's the common ground? What's going to make both inequalities true? If I plug in a value for x, that value of x is going to make both inequalities true at the same time. It's another characteristic of it being an and inequality. So let's see. If I go over here and I got a number line, let's deal with this first part. And let's say we got -1 right here. Well, we're saying that -1 in this case is greater than or equal to, that x is less than or equal to -1. Well, one, we got a closed dot, because it's a less than or equal to. And my graphic representation would be going like this, less than or equal to. And let's look at this second part. So here we're saying x is greater than or equal to -4. So let's say we got -4 right here. Now this is just a simple greater than, so I've got an open dot. And it's greater than, so my graphic representation would be headed to the right this way. But I got to make this the intersection. I got to put the two of these together. So let's see, let's do that. So we got a number line here. We got two critical points. We got a -4 and we got a -1. These would be called critical points on our number line. All right, and so the -4 is where x is greater than -4, and that's going to be characterized by an open dot. And the -1, we got x is less than or equal to -1. Well, that's going to be a closed dot. And it's an and statement, so I'm looking at the intersection. What would make both of those true? And it's going to be right here. Now let's look at an example why we have to do that. Because over here at the top we said that x could be any number less than -1. Well, let's say that x is -5. Well, if I plug in -5, let's see, to this. So let's set right here. So if I got 3 times -5, that's -15. -15 minus 2 is -17. Well, -5 is greater than or equal to -17. That would be true. But what if I put it in over here? Well, this is still -17. 3x, if I put 3 times -5 minus 2, that's -17. Well, -17 is not greater than or equal to -14. So anything over here would not be true. Let's look at the other end. Let's say I use 0. That's an easy one. Well, if I plug in 0 for x, again right here first, well, 3 times 0 is 2. I mean 0. And then I've got -5 is greater than or equal to -2. Well, that's not true. And so this would not be true. Let's pick a number right in here but where we're saying that we've got this intersection. Let's say -3. That's an easy one. Well, let's see. 3 times -3 is -9 minus 2. That's -11. -5 is greater than or equal to -11. That's true. Let's plug it into this second equation. So 3 times -3 is -9. -2, -11. -11 is greater than -14. And so that part is true. This is another way of thinking our way through how am I graphing this on this number line, which is, in other words, if it's an and statement, it's got to be a number that makes both inequalities true if that's plugged in for x. All right, later we'll look at compound inequalities with an or statement. Even more fun.